Hi, my name is Keith Dunnavant, Manager of Data Center Cooling Solutions for Munters in North America. And this is part 3 in a 3-part series on the Indirect Air Site Economizer. In this video segment, we're going to walk you through a sample data center case study. Specifically, we're looking at a data center located in Dulles, Virginia, at an elevation of 325 feet. Above sea level, we're looking at a data hall IT equipment load of 1,500 kilowatts that the cooling equipment needs to reject. It's going to be an efficient design with an external static pressure of the combined return air to the units and the supply air back into the data hall of only a ½ inch of water column. And we've selected as our peak design condition 100 dry bulb at an 84-degree wet bulb condition, and that's what we're using to size the trim DX cooling. We've selected the Munters Indirect Evaporative Cooling IASE type units for this particular project, and we're going to evaluate the performance in 3 operating scenarios. So we have System A, which we've selected a supply temperature for the job of 75 degrees Fahrenheit and a return of 95 degrees Fahrenheit, which is a 20-degree delta T. That's going to require 5 units to carry the load. So N equals 5, and each unit is rejecting 300 kilowatts of IT load. Operating in N+1 mode, normal mode we'll call it, they're rejecting 250 kilowatts each. At the peak, the trim DX for this system is 50 tons, and that works out to 53% of the total load that's required to be rejected, including the fan heat of the supply fans. Next, we've got a slight variation on System A. We're calling it System B, and it also is going to supply 75 under most operating conditions, but the temperature is allowed to drift up to 80 degrees Fahrenheit at the extreme conditions when DX would be required. So if it can achieve 75 degrees Fahrenheit supply temperature with just the indirect or dry heat exchange, it will do that. Otherwise, if it needs DX, it's going to let the supply temperature float up to 80 before DX is activated. So a little change there. So that means normally it will be having a 95-degree return, but at the extremes the return air temperature will elevate up to 100 degrees Fahrenheit. Still a 20-degree delta T, still the same in terms of the number of units required and the heat rejection capacity. But one key difference, since we're allowing the temperature to drift to 80 degrees, the onboard DX trim cooling has dropped to 33 tons, and so now that's only 35% of the total load. Next is System C, where we are going to hold a fixed 75 degree Fahrenheit with a 100-degree return. So the only change here is that we're increasing the delta T from 20 to 25 degrees, which has a significant impact in that now we can reject the load with only 4 units. Each unit has a capacity of 375 kilowatts in the peak or the critical mode, and under normal they'll be rejecting 300 kilowatts when all 5 units are operating. In this setup, we've got 54 tons of trim DX required per unit, which is 47% of the total. This is what the unit looks like, and I've walked you through this in the previous segment. We're showing here a rooftop installation, could just as well be a perimeter mounted installation, but you can see you've got your supply fans, filter, your heat exchanger, trim cooling coil, your refrigeration, your compressors, and isolation dampers here. This design that we've selected is capable of up to a max return air flow of 54,000 CFM. It's a nominal 50,000 CFM unit, and it can have up to 80 tons of onboard DX and it can optionally have chilled water as your trim cooling. Just to get you oriented in terms of the airflows, I'm only going to look at the system B in this situation. So we have a little pictorial here showing the condition 1, which is the return air coming back at 100 degrees Fahrenheit and a 70.4 wet bulb. So you've got actual CFM of 50,630. After fan heat, the temperature elevates up to 101.8, leaves the heat exchanger at 87.7, and that's at that 184 wet bulb condition. So your trim cooling is sized to take the air from 87.7 down to 80. So these are all of the airflows representative of that system operating in critical mode. Next, we have that same system operating in normal mode when your +1 redundant unit is operating. And here you can see that the airflows drop off quite a lot, both on the supply side and the scavenger side. And all that does is allow for lower internal pressure drops, lower fan power, and better overall performance. So you always want to have your redundant units operating when you can. This is a little bit busy, but it's necessary to walk you through that system B in terms of how we're going to evaluate it at bin weather conditions. So we have a table here. We've binned all 8,760 hours of typical meteorological weather data, TMY3 data for Dulles, and dropped it into bins. So you will see a bin number of hours, the mean coincidental dry bulb, and the outside air wet bulb condition. So when we bin the weather data, we bin it on wet bulb and then have a mean coincidental dry bulb tied to it, which is the appropriate way to do it when you have wet bulb driven equipment like our indirect cooling system. So we're looking at, I'm going to walk you through this at various conditions, but here you see that at the peak conditions we're supplying air at 80, it's returning at 100. The indirect cooling system is doing 75% of the work, or 75% of the total. It's got a coefficient of performance of 6.3, and the partial PUE at this bin condition is 1.169. And here's your water utilization effectiveness, 1.46 at that condition. As you see the temperature of the outside air dropping, so we're dropping down 94, 88, 85. When we finally get to a 73 wet bulb at this point, to achieve that 80 degree supply, we're able to do that 100% with indirect. So you'll see that pretty soon now the temperature will begin to drop, and by the time we're finally down at a 67 wet bulb, we're able to bring that temperature on down to 75 degrees Fahrenheit. So there are these bins, you can add them up yourself, to the 76.2, 451 hours, 393 hours, and so on, that we would be operating above that 75 degree supply temperature. But we're pretty quickly dropping on below 80 degrees and getting to that 75 target supply rapidly. So we've selected 4 different operating points, the 74.9 and 69 condition, and then here's a mild winter condition that we're going to look at in a minute. You can see that the coefficients of performance are increasing rapidly, meaning the system is performing more efficiently. So we're already up to 15.8, and then at the extreme winter we're as high as 17, a coefficient of performance. We're turning the water off at 50 degrees Fahrenheit, so that resulted in this bin of 49.1 and 43, where you see water utilization effectiveness go to 0. Here we're looking at the operating profile for System B, and the way you read this chart is on this x-axis here is the ambient wet bulb bin condition. And you've got the bin hours on the right vertical axis and kilowatts consumed on the left vertical axis. So if we start out here at 81 wet bulb, there was only 1 hour of operation. As the wet bulb is decreasing, you'll see there was a lot of hours here at this, about 69 wet bulb, and the number of hours is decreasing. So the yellow line is the number of hours at each wet bulb bin. On the, now we're going to walk you through what the power consumption looks like for each of the components that are consuming power in the indirect air side economizer. So starting from the bottom up, we have the supply fan power. And you'll see that's a flat line. We're assuming that the data center load is constant, so the supply fan power is constant. And this is operating in the normal mode when your N+1 unit is running. So the supply fan is consuming, or the supply fans, this is for all units. And in this case, we've got 6 units running. So we're consuming less than 100 kilowatts of supply fan energy for the total 1,500 kilowatt load. Next, we have the pump power. So here's your little segment of pump energy that's being consumed. And you'll see that the pump power shuts off. We turned the water off at 50 degrees Fahrenheit. So you'll see that that tapers off. Next is the scavenger fan energy. So at the peak, wet bulbs, it's working the hardest. It's got to pull all of that heat out of those tubes. And so it is pretty flatline until finally, when the wet bulb gets to a point where you've got excess capacity, it begins to taper off, and it reduces really quickly with falling wet bulb. So as that wet bulb is declining, you need less mass flow of scavenger air to flow over those wetted tubes to extract the heat. So that's a really key element of a wetted heat exchanger. So you see how well that declines, and it diminishes to very, very low values until we turn that pump off, and then you'll see a pickup. So the pump power drops off, but you see a pretty good bump in scavenger fan energy, and that's because we're now working with a dry heat exchanger. This heat exchanger is 55% effective, dry to dry, but that's nowhere near as effective as the wetted heat exchanger efficiency. So it takes a little bump, and you get a little uptick in scavenger fan power, and then as the ambient temperature falls, you'll see that continue to decline until finally at these extremes it's actually doing heat rejection in natural convection mode, and it's completely off. Next is the compressor power, and at the peak wet bulb, and certainly the design wet bulb conditions, the compressor power can be the highest consumer of power. So here's your compressor segmented power, and you'll see how that declines with falling wet bulb until that's completely turned off. So that's a little overview of how these systems run, and the important thing to note is that the supply fan energy for most of the year is the highest consumer of power, and that's really a very critical component that you want to pay close attention not only to your supply fan power efficiencies and motor efficiencies, but also anything you can do to reduce your connected resistance to airflow. Your external static pressure is going to pay huge benefits. So now I'm going to look at the operating performance summary for the 4 ambient conditions of the solutions A, B, and C. So this is operating in normal mode where you've got your N+1 units running. And here's your operating kilowatts for the whole 1,500 kilowatt load that we're rejecting. So it's all units are operating. So solutions A and B would have 6 units operating. You've got N equals 5, N+1 is 6. And solution C has 5 units operating, N is 4, N+1 is 5. So here you can see that the solution A is consuming the most power at an 88 Fahrenheit dry bulb and 81 wet bulb. You can read that and you'll see that as we drop to system B, letting the temperature float up to 80, we use less compressor power, so it has a lower total power consumed at that extreme wet bulb condition. That was the highest wet bulb bin. But you'll see that solution C was a little bit higher in the kilowatts, and that's only because we were holding fixed that 75-degree condition with that lower delta T solution. Then you can watch it drop. So at the 74.9 and 69, you see the overall power that's being consumed to reject the load tapering off. So as it's getting more and more mild, you'll see that at finally when we're at only 3.8 degrees Fahrenheit, we're consuming less than 100 kilowatts of power to reject that 1,500 kilowatt IT load. And at this condition, your solution C is the most efficient because we've got that higher delta T to benefit us. Here is a summary of the annual performance. So we've got an estimate of annual electricity consumed in kilowatt hours. So system A, 1,092,000, system B, 1,027,000, and system C, 915,000. So system C is the overall winner for the annual power consumed. In terms of water consumption, you'll see that you've got 4,215 cubic feet of water consumed by solution A, 4,339 by system B, and 4,056 by system C. And to help you understand some of this, it has to do with the fan heat addition. So the reason this drops off is that it's doing by having the benefit of the higher delta T, there's less fan power to circulate the air, and that has an impact on the fan heat that has to be rejected, and so that's why that number is a little bit lower. And here's your estimated partial PUEs annualized. So we've got very nice low partial PUEs, 1.083 for system A, 1.078 system B, and 1.07 for system C. Lastly, we're going to look at the critical mode operating performance. And this is going to be a summary of now peak kilowatts consumed by each of the different systems. So for system A, which was a 75 to 95 machine, 300 kilowatts, its peak kilowatt consumption is 90. And that is per machine. The COP is 3.63, so we've got 5 machines running at this critical mode and still operating pretty efficiently. At system B, we're letting that temperature float up to 80, and you'll see that the reduction in compressor power helped to bring this peak kW down to 76 and elevate your COP up to 4.32. System C sees a peak kW of 95 kW, but remember there's only 4 units running with system C, so it's still a very, very efficient system. All right, and then I thought you'd be interested in this last system D, And specifically, what would happen if in the System C design, we also let the supply temperature drift to 80 degrees Fahrenheit at the extreme wet bulb conditions. And so normally it would run from 75 to 100, but at the extreme wet bulbs, it would drift to 80 degrees and the return would go to 105. That allows us to further downsize the DX, and now we have the peak kW dropping all the way down to 80 kilowatts times 4 units, 320 kilowatts total, COP of 5.02, very efficient system. Lastly, we're going to look at the sizing of the water storage tank required. Since for these designs we have only included what we call trim DX. So that's the amount of refrigeration to reject the load at the peak wet bulb condition while indirect evaporative cooling is running. So we're depending on the performance of the indirect cooler under all conditions. So we need a guaranteed source of water. So if you don't have a guaranteed source of water, then you need to put in some water storage to allow for water to be supplied to these units during a critical mode of operation. So normally you would size a storage tank for a peak 24-hour period. So we look at all 8,760 hours of the typical TMY3 and we select the worst case 24-hour segment of water consumption. And that varies a little bit from city to city, but for Dulles, Virginia, a good metric to use is 10 gallons of water consumed per kilowatt of load. So your water storage tank required is 1,500 times 10, 15,000 gallons of capacity for this 1,500 kilowatt load. And that'll cover you for the worst case 24-hour period on a loss of water. That's it for this segment. Thank you for watching, and please visit our website for more information.